Welcome to G Fun Facts Online, the show where we dig deep into the science that shapes our world. Look around you at the soaring skylines of our cities, the massive bridges that leap across rivers, the tunnels that dive beneath mountains. These are monuments to human ambition, gleaming structures of steel and glass. But have you ever wondered what holds it all up? What prevents these concrete giants from sinking, tilting, or collapsing? The answer lies hidden beneath our feet, in a field of engineering that is one of the most important yet least celebrated disciplines in the world. Today, we're pulling back the curtain on the unseen world of geotechnical engineering, the science of ground truth. When you build a billion-dollar mega-project, you aren't just building on land. You are building on a complex, unpredictable mix of soil, rock, and water. Geotechnical engineers are the detectives who investigate this hidden world. They figure out how the ground will behave under immense pressure and design the foundations that make the impossible possible. From the tallest skyscraper to the longest tunnel, they are the unsung heroes who ensure our world is built on a solid foundation. So, let's start digging. Let's begin with the quintessential symbol of urban progress, the skyscraper. Imagine a vertical city, weighing hundreds of thousands of tons, all balancing on a relatively tiny patch of ground in a crowded city. The challenge is immense. The entire weight of that building has to be safely transferred deep into the earth. If the geotechnical engineers get it wrong, the consequences are catastrophic. Two main things keep them up at night: bearing capacity and settlement. Bearing capacity is simple. How much weight can the ground handle before it fails? Settlement is how much the building will naturally sink into the ground over time. A little is expected, but too much or uneven settlement can spell disaster. To solve this, engineers don't just build on the surface soil, they go deep. The most common solution is a pile foundation. Think of these as incredibly strong stilts, long columns of concrete or steel that are drilled or hammered deep into the ground until they hit a strong layer of soil or solid bedrock. They transfer the skyscraper's load past the weak surface layers to something much more stable. For truly massive structures, they might use caissons. These are huge, hollow, watertight boxes that are sunk into the ground and then filled with concrete, creating a single, colossal foundation leg. Often, modern skyscrapers use a hybrid system called a piled raft foundation. This combines a thick concrete mat, or raft, that spreads the load over a wide area, with deep piles that anchor it securely. It's the best of both worlds. But what about the case study to end all case studies? The Burj Khalifa in Dubai. Soaring over 828 meters high, it's the tallest building in the world. And it was built on some of the worst possible ground you could imagine: loose sand and weak rock, with a high water table. The geotechnical investigation was one of the most extensive ever done. The final design was a masterpiece, a 3.7-meter thick triangular concrete raft, supported by 192 piles, each 1.5 meters wide and plunging 50 meters into the ground. A major concern was the wind. The constant pushing of wind against the tower could, over years, degrade the grip of the piles and the soil. So they ran extensive tests, simulating decades of wind loading to ensure the foundation would hold firm. The result: the Burj Khalifa has settled even less than predicted. It's a monumental success story for geotechnical engineering. Now, let's move from building up to building across. Long-span bridges are another marvel. They don't just have to support their own immense weight and the constant flow of traffic. They have to resist powerful side forces from wind, water currents, and even earthquakes. And they're often built in incredibly difficult environments, like deep water or on steep, unstable slopes. Again, the solution is deep foundations. Caissons are a favorite for bridge piers in the middle of a river. These massive concrete structures are often built on land, floated into position, and then sunk to the seabed, creating a solid base to build upon. Sometimes they use cofferdams, which are like temporary, portable dams that create a dry workspace on the riverbed so foundations can be built. Let's look at the Millau Viaduct in southern France, one of the tallest bridges in the world. It elegantly crosses the Tarn Gorge on 7 incredibly slender piers. The challenge here was that the ground was different on either side of the valley. One side was limestone, the other, weaker marl rock. The bridge is extremely sensitive to any settlement, so the foundation design had to be perfect. Each giant pier is supported by 4 massive shafts drilled deep into the rock, between 9 and 16 meters deep. For the piers on the weaker marl side, the design was especially cautious, and they used an observational approach, constantly monitoring the foundation's performance during and after construction. The result was a stunning success, with tiny, acceptable amounts of settlement, proving that engineers can handle even the most complex and variable ground conditions. From building up and across, we now go under. Tunnels are the arteries of modern infrastructure, carrying trains, cars, and utilities beneath our cities and through mountains. Tunneling is perhaps the most uncertain of all megaprojects. You are literally moving into the unknown. The biggest challenge is the variability of the ground. A tunnel might start in hard, stable rock, and then suddenly hit a soft, waterlogged fault zone. A detailed geotechnical investigation creates a ground model to predict what they might find, but surprises are almost guaranteed. When tunneling through hard rock, the main goal is to stop it from collapsing. Engineers use a combination of rock bolts, which are like giant screws drilled into the rock, and shotcrete, a type of sprayed-on concrete, to stabilize the tunnel. But soft ground, like sand or clay, is a different beast. Here, the primary concern is preventing the ground from moving and causing the surface above to sink, which could damage buildings and roads. This is where tunnel boring machines, or TBMs, come in. These are engineering marvels in their own right. Think of them as giant mechanical worms. At the front, a rotating cutting head chews through the earth. As the TBM moves forward, it simultaneously installs a precast concrete lining behind it, providing immediate support and minimizing ground disturbance. The perfect example is the Channel Tunnel, the 50-kilometer rail link between the UK and France. Its success hinged entirely on geology. Years of investigation identified a perfect layer for tunneling: chalk marl. It was soft enough to be easily excavated by a TBM, but also strong and impermeable enough to be stable. 11 custom-designed TBMs chewed their way under the English Channel, but it wasn't all smooth sailing. They still hit unexpected zones of fractured, water-bearing rock. To overcome this, they used incredible techniques like ground freezing, where they pumped refrigerants into the ground to freeze the water and stabilize the rock before tunneling through it. The Channel Tunnel is a testament to what's possible when you combine meticulous investigation with adaptive engineering. Finally, it's not just about building, but about holding back. Dams are some of the most impactful projects on Earth, but they also represent enormous risk. The stability of a dam is fundamentally a geotechnical problem. A key issue is seepage. Water will always try to find a path through and under a dam. The engineer's job is to control that seepage, often with a core of low permeability clay and internal drainage systems. If uncontrolled, seepage can cause internal erosion, a process called piping, which can lead to catastrophic failure. The Three Gorges Dam in China, the world's largest power station, faced enormous geotechnical challenges. It's built on a massive granite rock mass, but one that is riddled with geological faults. An immense investigation was undertaken to map these weak zones, which were then excavated and replaced with concrete, and the surrounding rock was strengthened with grout injections. The entire future of this field is being transformed by technology. Building Information Modeling, or BIM, creates a 3D digital model of the ground, integrating all the geological data so engineers can see the whole picture. Artificial intelligence and machine learning are being used to analyze vast data sets and predict how soil will behave, reducing the risk of unforeseen conditions. And remote sensing, using satellites, can now monitor ground settlement over huge areas with millimeter-level accuracy. We can embed Internet of Things sensors directly into foundations to get real-time data on their performance, creating a digital twin of the structure. Geotechnical engineering is about more than just technology and calculations. The decisions made by these engineers have huge economic, social, and environmental impacts. Getting it right saves billions of dollars. Getting it wrong causes delays and disasters. Choosing the right methods can protect communities and minimize environmental damage. These mega infrastructure projects that define our modern age are built on a foundation of trust. Trust in the materials, trust in the design, and ultimately, trust in our understanding of the ground itself. That trust is earned by the geotechnical engineers working tirelessly behind the scenes. They provide the essential ground truth that allows us to build higher, span further, and dig deeper than ever before, ensuring our future is built on a solid, safe, and sustainable foundation. Thanks for tuning in to G Fun Facts Online.